Hello, my name is Sihao Cheng. I'm a graduate student at Johns Hopkins University. Today I'm going to talk about the scattering transform, which I think is a powerful new approach to observational cosmology. I will start with a general question. How do we characterize a physical field? So for example, in cosmology, we have the density fluctuation field, and in astrophysics in general, we have maps of ISM emission and the galaxy images. So from these images or fields, we oftentimes want to know the physical parameters behind it. And in our daily lives, we have similar tasks. For example, from this image, we wonder whether there's a cat or a dog in it. So these tasks are actually quite difficult because of its huge generic richness, or in other words, the dimensionality of a field, especially random field, is very high. So in order to do this, people usually first extract features from a field and then do the regression from features to physical parameters. And this dimensionality reduction requires a domain knowledge input. So for example, if we know the CMB map is very close to Gaussian, we use power spectrum to extract features. And if we know a field is not far from a Gaussian random field, we can do the endpoint correlation expansion. Or in the late time universe, for example, we know the density map is mainly composed of halos, so people tend to use cluster counting method. And the CNN convolutional neural net, which is a rising method, recently showing great success in computer vision and try to learn features by itself. This feature extraction can also be called as finding a representation of the field or characterization of the field or calculating statistics of it. On the one hand, it's interesting to ask, so is there any general domain knowledge about physically relevant fields? And indeed, we have some intuition about physical fields. For example, we usually see localized features in it. It's multi-scale, and it's driven by long-range physical interactions. And usually you also see hierarchical structure forming in it. And on the other hand, the success of CNN suggests that perhaps CNN is implicitly making use of these domain knowledge of physically relevant fields. There are two special things of CNN. One is that it restricts all the operations to be local convolutions. And the other is that it extracts features after it learns features from a large training set. So if its success is also relevant to the first special thing of CNN, that means perhaps we can design some new statistics sharing the success of CNN, but without the need of doing training on a large sample. The scattering transform is exactly designed following this idea. So now let me have a brief introduction of how the scattering transform works. From the original image, the scattering transform apply one operator several times. So this operator is composed of wavelet convolution and a modulus operation. And so it generates a series of images by convolve the original image with a different wavelet. And then from each image generated by this scattering transform, you can apply the same operator again to generate another series of images. And finally, in order to generate a translation invariant estimator of the field, we can just simply take the mean value of all of these images generated from the original one. So intuitively, the scattering coefficients are similar to the power spectrum of the previous order image. So for example, for the first run of these scattering transform, the coefficients here are close to the power spectrum of the original field. The second order coefficients are similar to the power spectrum of the first order images instead of the original image. In this way, the second order coefficient actually contains some information beyond power spectrum of the original image, and that is to say it extracts some non-Gaussianity of the original image. So now let me go to some detail of these operations. The first one is the wavelet convolution. So what is a wavelet? Wavelets are localized waveform in real space and window function in Fourier space. So wavelets within one family have different scales and directions, but they all have the same shape. The scattering transform by default use Molet wavelet, which have a Gaussian profile in the Fourier space. And the family of wavelets will cover the whole Fourier space. Therefore, convolve the original image with a wavelet is, in essence, selecting a scale of fluctuations. And because the wavelet is complex valued, the convolved image is also complex valued. So it can be decomposed into its modulus and its phase part of the complex numbers. And the second operation of the scattering transform is taking only the modulus and abandoning the phase. This operation is actually converting the fluctuation into the local strength of the fluctuations. And finally, the scattering transform takes the mean of these convolved and modulus the image. These operations actually remind us of the power spectrum, and indeed, the power spectrum can be defined in this framework too. So if we convolve the original image with a Fourier eigenmode, and what we get will be just another Fourier eigenmode, and the only information is the initial phase. So then if we take the modulus, we have a uniform image, and then take the mean, that will be the square root of the power spectrum at the frequency k of the convolutional kernel. And if we compare these two methods, the wavelet convolution plus modulus and the power spectrum, we'll see that they are very similar. So both of them are extracting the strength of fluctuations at one scale, but they're also different. So first, the scattering coefficients defined in this way are always proportional to the original field. So in some sense, they are first order estimators, but the power spectrum is second order of the original field. And more importantly, by doing a wavelet convolution, we still keep some spatial information in this plot here. But if we convolve the image with a Fourier eigenmode, we remove all the spatial information. And this important difference enabled the scattering transform to be applied iteratively to extract more coefficients. So although in the first iteration, the scattering coefficients and the power spectrum are very close to each other, starting from the second iteration, we extract a significant amount of non-Gaussian information. So now let's have an intuitive understanding of the coefficients of scattering transform. So as we mentioned previously, the first order scattering coefficients is very similar to just a low resolution power spectrum analysis of the original fields. And they are measuring the clustering of kind of particles in the original field. But the second order coefficients are similar to the power spectrum of the first order scattering images. And as we know, the first order images are highlighting the positions with oscillations at particular frequency. So they're kind of, the first orders select some structures at one frequency, and the second order coefficient is measuring the clustering of these structures instead of single particles. So in this way, the second order scattering coefficient actually includes information of up to 4-point correlation functions. And in general, if we iterate the scattering transform n times, it's measuring the clustering of structures, and it actually quickly includes information up to power n point correlation functions. On the right-hand side, I'm showing a visualization of the scattering transform using simulated weak lensing convergence maps. They all have the same power spectrum. So as expected, the mean intensity of the first order scattering images are similar, but although the total intensity are the same, but the distribution of this intensity in the first order are already very different. So that's why if we do the scattering transform another time in the second order, that can be extracted by the scattering coefficients. Here we see that for the Gaussian random field case, the structures are not clustered particularly, but for a weak lensing convergence map, the clustering of structures is very clear. The second order scattering coefficients can be seen as some measure of non-Gaussianity. And here it's almost the same story, just I'm showing the distribution of the second order scattering coefficients as a function of the scale of the first wavelet and second wavelet. And the left-hand side is a famous degeneracy between omega-8 and sigma matter from a weak lensing measurement. Basically, the power spectrum is sensitive to this direction. It's an overall change of clustering strength. But if you move along the degeneracy, power spectrum doesn't change. But we see that the second order coefficients here are particularly sensitive to the change along the degeneracy. And this sensitivity can be translated into the constraint of cosmological parameters. The gray ellipse here is the constraint from power spectrum, and the blue one is showing constraint from first order scattering coefficient. They're very similar. But if we add the second order constraint, we see that improves, it breaks the degeneracy. So these results are for ideal noiseless convergence maps simulated from embodied simulations. Of course, if we add galaxy-shaped noise, all the constraints will degrade. But again, we see the scattering transform will provide a much tighter constraint than the power spectrum. And if we compare the constraint from scattering transform and CNN, we see that they're actually very close to each other. And this is the comparison. So this means perhaps the scattering transform already extract all useful information. To summarize, we have introduced the scattering transform, which is a new statistics borrowing ideas from a convolutional neural net, but it needs no training, and it shares also the advantage of traditional statistical analysis. And the scattering transform have a similar structure to convolutional neural net. It's composed of wavelet convolution plus a modulus operation, and do it several times, and finally take the mean of all the images generated by the convolution and modulus. So it has several advantages to traditional statistical estimators such as three-point function or bispectrum. First, it is efficient. That means it concentrates information into fewer statistical estimators. For example, in our weak lensing analysis, we only have 37 estimators. And this is achieved by two binning strategies. One is binning in Fourier space. That's because the wavelet, the family of wavelets, is basically a logarithmic binning in Fourier space. And that make the number of estimators much fewer, and it concentrates information, and it makes also each estimator more stable. The second is the binning strategy of multi-point informations. For example, to the second order scattering coefficients includes up to 4-point functions. Although at the beginning, like in the power spectrum case and the first order scattering coefficient case, the binning seemed to be trivial. It is not at all trivial for higher order information, because the possibility of all different configurations increases very quickly, but the amount of data which limits the signal noise does not increase. The second advantage is its robustness. Even if we iterate the scattering operation several times, all the coefficients are still just proportional to the original field. So they're, in some sense, first order estimators, as opposed to the endpoint function. And also the scattering statistics is interpretable. It can be explained as clustering of structures. And we've shown in simulated weak lensing convergence map that the performance of the scattering transform to constrain cosmological parameter is on the par with CNN and much better than the power spectrum alone. And on the right-hand side here is a visualization of how the scattering transform extracts non-Gaussianity from weak lensing convergence maps. Besides weak lensing, I think there is a potentially broad application of the scattering transform in cosmology and astrophysics. As in the late-time cosmology, we know that the non-Gaussianity of many fields are high, and also in astrophysics in general, there are a lot of non-Gaussian fields, which is hard to deal with using traditional statistics. Yeah, thank you for your attention. I'm looking forward to our discussion.